this video, we're actually going to calculate the standard error of the mean so you can see how that's done. Okay, so let's start with a problem. The population of scores on a high school test of science knowledge forms a normal distribution with mu equaling 500 and sigma equaling 100. So right up front, we know the population mean and we know the population standard deviation. We don't have to do any estimation at all. It's given to us. If you take a random sample of n equals 25 students, what is the probability that the sample mean will be greater than a mean of 540? Okay, so what are the steps for solving this problem? Well, it's really just two steps. The first one is to calculate the standard error of the mean, and that's the average amount we expect sample means of a particular sample size to deviate from the population mean. The second step is to calculate the z-score for the sample mean. So here's our formula for calculating the standard error of the mean, and we get this from the central limit theorem. And we just plug in the numbers that are given to us in the problem. So the population standard deviation is 100. The sample size is 25, and we're going to take the square root of that. Okay, so the square root of 25, of course, is 5. So really that amounts to 100 divided by 5, and that equals 20. So our standard error of the mean is 20. And what does that mean? Well, what that means is that given a sample size of 25, we expect sample means in the sampling distribution to differ from the population mean, to deviate from it by 20 points on average. Now our second step then is to create or to compute the z-score for the sample mean that we've observed. Okay, so you'll look at this formula right here, and it looks really pretty similar to what you've seen for a z-score for individual raw scores, right? The big difference is that in the denominator, we no longer just have the standard deviation of the raw score. Now what we have is the standard error of the mean, okay? So the denominator is a little bit different. In the numerator, right, we have the sample mean rather than x. So there's a little bit of a difference in the formula, but the overall structure and format is pretty much the same. And the good news is we can pretty much interpret it the same as well. So let's go ahead and plug in our numbers. And what we get now is 540, that was the sample mean, minus the population mean, which is 500, right, divided by 20. Okay, so when we work that out, that becomes 40 over 20, or positive 2. So what that means is that the sample mean for the group that we observed ended up with the sample mean was 2 standard errors above the population mean. So these are folks who did pretty well on this test of science knowledge. Now let's go into the normal distribution, or the sampling distribution, which is normally distributed, and locate where 2 standard errors is above the mean, right? Well, it's right here, right? Because each standard error was 20, right? We calculated the z, which was 2, and that then, of course, is going to correspond to the mean for our sample, which was 540. Now, to answer the question, what is the probability of observing a sample mean of 540, we just need to take this area that's above a score of 540, right, and just say, okay, you know, what's the likelihood that we're going to see scores 540 or higher just randomly drawn from that population? And that area, when we look into a z-table, constitutes only 0.0228 of the area under the curve, okay? So the likelihood that we get a score of 540 or higher observed randomly is really pretty slim, okay? And you might say, well, it's only 40 points higher, right, than a score of 500. It doesn't seem like it would be that unusual. What you have to keep in mind here is that this is a mean we're talking about, right? So it's a mean of an n equals 25. That's different than saying an individual raw score. So even though you might draw, you know, extreme raw scores every now and then, to get a mean of n equals 25 that is that much bigger than the population mean is really pretty unusual, okay? Okay, so big picture, sampling error is the difference between a sample statistic and a population parameter. The standard error is the average amount sample means are expected to deviate from the population mean, and we calculate the standard error of the mean. So you can interpret that standard error as the standard deviation of the sampling distribution. And then the probability associated with the z-score for a sample mean tells us the likelihood of randomly observing a mean of a given value drawn from that sampling distribution. And of course, every sampling distribution has an assumed sample size, or n. Okay, so if you change the n, you'll effectively change the nature of the sampling distribution as well. Okay.